So Descartes' rule and conjugate root theorem. This is where you'll be able to find complex zeros and also write polynomial functions, okay? So now, up to this point, you have been given polynomial functions, you found zeros, you graphed these polynomial functions. Now we're gonna go the other way. Now you're gonna be given, the zeros, and you're gonna have to write equations, okay? So we're going backwards now. We're also going to be looking at complex zeros. Complex zeros are the ones that have imaginary numbers involved. They're also the ones that have like radicals involved as well. Okay, so these are examples of complex zeros. Descartes' rule basically says that if you have a polynomial function with real coefficients, okay, if you have a polynomial function with real coefficients, then the number of positive real zeros of f is equal to the number of variations in signs of f of x, or less by some even number. So the number of positive real zeros, possible positive real zeros, is equal to the number of variations in signs of the original function, or less by some even number. And the number of possible negative real zeros of the function is the same as the number of variations of signs of f of negative x, or less than that by some even number. So what that means is that your zeros, they're going to come in essentially like in pairs, okay? So that's why it says it's going to vary or less by some even number. Variations of signs means when you look at the original function, does it change from positive to negative, or does it change from negative to positive? If so, then that counts as a change. So then you would count those. How to apply Descartes' rule is those steps that you guys see on the next, I think actually below, where you just wrote some stuff in. It looks like a lot, but it's actually very simple once we look at the examples. But you want to look at the original polynomial function and its signs. Count how many times the sign changes from positive to negative or negative to positive. However many that is, that's the maximum possible number of positive zeros. Then you count down by 2 to find the possible number of positive real zeros. Once you've done that, next look at f of negative x. That means you're going to plug a negative x into your function and you're going to simplify. After you simplify, when you plug the negative x, then you count the number of sign changes in f of negative x. That is the maximum possible number of negative zeros. And then again, you count down by 2 to find all of them. This rule basically tells you, again, the possible number of positive and negative real zeros that you can have. So we're going to look at some examples. We'll look at 2 together, then I want you to try the other ones on your own. So here's your original function. Step 1. It said to look at your original function and then to count how many times the sign changes from positive to negative or negative to positive. So here, does it change from here to here? What about from here to here? What about from here to here? You're looking at the sign. Is it a positive number or a negative number? Does it change from here to here? Yes, I go from positive to negative. What about here to here? Yes. Does it change? Does it change? So this right here, there's only 2 changes. That is the maximum possible number of positive zeros. Okay? So possible positive zeros, the max is going to be 2. Then it says count down by 2 to find all the possible number of positive zeros. Well, when I count down by 2, what's the next one? Like, what's 2 minus 2? 0. So this is basically saying I could have 2 positive real zeros, or I can have no positive real zeros. That's steps 1 through 3 in Descartes' rule. Steps 4 through 6 tell you how to find the negative ones. Yes?
So more like a minimum maximum.
Exactly. Because first off, how many zeros could I potentially have here? I can have 7, because that is the largest exponent in my polynomial. Descartes tells me how many positive ones I could possibly have and how many negative ones I could possibly have. Okay? Now to find my negatives, I need to plug in a negative x into the function. That's what it says. Next, look at f of negative x. So that means I need to plug a negative x in for all of my x's in my polynomial function. I wrote too big because now I'm running out of space. And then you'll want to simplify. A negative x raised to an odd power gives you a positive or a negative? Question mark. A little loud. It gives you a negative. So this becomes negative x to the 7th. When I multiply by a positive 4, that turns into a negative 4x to the 7th power. But when I raise a negative x to an even power, is that positive or negative? It's positive, so this becomes a positive x to the 6th. When I multiply by a positive 3, it gives me a positive 3x to the 6th. You want to simplify after you plug in your negative x. What's negative x to the 5th power? It's negative x to the 5th. There was a positive on the outside, so it turned into a negative. What's negative x to the 4th power? Positive. So that becomes a positive 2x to the 4th, because again, a positive times a positive is positive. This one, the next one, negative x to the 3rd power is a negative x to the 3rd power, but because there's a negative on the outside, it becomes positive. Continuing forward, that will give me a positive x squared, a negative x, and a positive 1. You're going to want to simplify after you plugged in the negative x. Because once you do that, then again, you count the sign variations. Does it change? Yes. Does it change? Yes. Does it change? I'm saying, does it go from positive to negative, negative to positive? Which it does. Every single one of these it does. Does it change? Does it change? Does it change? Yes. Does it change? How many is that? So the maximum number of possible negative zeros, the maximum number is 5. But again, we count down by 2s to find all the possible ones. So what's 5 minus 2? And what's 3 minus 1? Oh, 3 minus 2?
1.
1. And of course, you wouldn't put 0 after that because 1 minus 2 is a negative 1 and we can't have that. So, since this is a polynomial to the 7th power, Descartes' rule basically tells us again that the possible number of positive real zeros I can have is 2, the maximum, and the possible number of negative real zeros that I can have is 5. But I can also have 0 positive, or 3 negative, or 1 negative. Okay? So again, number 2, I look to see if it changes. Starting from here, does it change? Does it change? Does it change? Does it change? So from the original, my possible positive real zeros are going to be 3 or 1. Because you count down by 2s once you find your maximum. Now to find my negatives, I need to plug in a negative x. I'm showing this step to make sure that everybody can see how and why some of the signs may change when I plug in a negative x. Will I do this on my key? I probably won't show this line, but I'll definitely show what the simplified line is of the negatives, okay? Again, a negative raised to an even power is a positive, so you just gotta multiply it to the coefficient on the outside. Raise it to an odd, it's a negative, you multiply it to the outside. Even turns into a positive, but since this is a negative 7 to start with, it becomes a negative 7x squared. Negative and the positive make a negative. Here we go. Does it change? Does it change anywhere else? So then, my possible negative real zeros is only 1. The rest are on you. The rest are on you. Online, how many possible positive zeros did I have? Anyone online?
4, 2, and 0.
4, 2, and 0. You guys agree? Yes, I have 1 change, 2 changes, 3 change. All 4 of them change. So then you count down from there. Now, when I plugged in the negative x to get my function, you should have had 6x to the 4th plus 7x to the 3rd plus 8x to the 2nd plus 7x plus 2 when you plugged in that negative x. Yes? So test what, how many possible negative real zeros do I have? I have 0. There are no changes at all. Very good. Sid, how many possible positive real zeros do I have in number 4?
I have 2 and 0.
2 and 0. Online, do you agree?
Yes, ma'am.
Yes, ma'am.
Okay, good, because you have 1 change here and then another change there, okay? And I plug in the negative version. That'd be x to the 6th minus 2x to the 4th minus x squared plus 2. It's the exact same as the original. Flashback to unit 1. If I plug in negative x and I get the exact same thing as the original, this particular function is a what function?
Even function.
It is an even function, yes. But don't forget things from earlier units. So then online, somebody different than who responded to the first one. How many possible negative real zeros do I have?
Two, 0.
2 and 0.
2 and 0, yes, because again, I have a change here and I have a change here, wonderful. And for the last one, online, somebody different. How many possible positive real zeros do I have?
4, 2, and 0.
You guys agree? Yes, I have a change here, a change here. 1 here and 1 there. Perfect. I plug in the negative. That gives me a negative x to the 5th minus x to the 4th minus 3x to the 3rd plus 9x squared plus x plus 5. In the classroom. How many? 1. I just have 1? Right here. Perfect. Do you notice anything between your maximum possible real zeros And your maximum negative real zeros, Colton?
So always add up to like your highest exponent.
Exactly. It always will add up to your highest exponent. 4 plus 1 is equal to 5. If it's 6, ooh,
That, I was gonna say like the majority of the time.
majority of the time it does. Okay.
Is it because like this one is missing like an x to the fifth?
Exactly. This one's missing a few terms, missing an x to the fifth, an x to the third, and an x. This one wasn't missing anything, so it held true. Let's look at number 3. Was it missing any terms? The highest one was a 4. 4 and 0 make 4. So you can at least say if you have all your terms, the maximum should add up to be the total. So when that happens, then that means the other 2 zeros have got to be what? Because I should have a total of 6. This one here says I only have a total of 4 real ones. They're imaginary. And that's where the conjugate root theorem comes in a way, and how that is even possible. Okay? So go ahead and get the cards in. The next one is conjugate root theorem. You are going to have to write this first part by hand. Then the examples are actually in the foldable. Conjugate root theorem says that if the imaginary number a plus bi is a root of a polynomial equation with rational coefficients, then its conjugate, a minus bi, is also a root. Remember, root is another word for 0, okay? So in other words, imaginary numbers, complex numbers, they come in pairs, okay? So if you have one that's a positive, then you know automatically its negative is also a root of that polynomial function. So if a polynomial has the following given roots of negative 4i and 2, this is not a polynomial that has a degree of 2. It's actually a polynomial that has a degree of 3, because there's one more 0 that's there, it's just not written down. What's that other 0? If you have, say again, it would be 4i. And the reason why it's 4i is because that is its conjugate. If you have the negative version, then the positive version is also a root. And it's only the imaginary part that changes with the conjugate root theorem. So for example, like in number 2, you have 3 zeros here, or at least that are written down. You have 4 minus 2i. Its conjugate would be 4 plus 2i. You only change the part that's imaginary, you only change the b part, okay? 4 is a real number. Real numbers don't have pairs unless it tells you that it's a double root or something like that. But 8i, negative 8i would be its other root, because again, they come in pairs. So number 2 is not a polynomial with a 3rd degree, a cubic. It's actually a quintic because it actually has 5 roots, 5 zeros. Only one of them is real though. If I look at number 3, what will be the degree of this polynomial in number 3? It'll be 4, because 1 0 is 1 minus 3i. The second 0 is 2i. What's the third one? 1 plus 3i. And then the fourth one would be negative 2i. Okay, so anytime you see an imaginary number or complex number, they always have a pair. This last one, this has a degree of what? It will have a degree of 4. 8 is a real number, it doesn't have a pair. 4 is a real number, it doesn't have a pair. I has a pair, what's the other one? Negative I. And like I said before, the same thing applies with complex numbers. Like if you had the square root of 3 and then 2 minus the square root of 2, the other zeros would be what? Works the same way. Don't overthink it. So remember when we take the square root of something, we get plus or minus that number. The same concept. Same concept with the complex ones as well. So they always come in pairs. That's why in that one problem, when we only saw that we have 4 real zeros, well, that's because the other 2 were imaginary. They were that pair together to make a total of 6. So we're going to write a blank polynomial with rational coefficients with the roots 3 and 1 plus I. In your foldable, you don't have what degree it is, nor do you have the actual roots on your paper. So you're actually going to have to write in both things. You're going to have to write in the roots, and I want you guys to tell me what degree polynomials is going to be. Looking at your zeros. It's going to be a cubic polynomial, or 1 to the 3rd degree, because my zeros are 3, 1 plus I, and also 1 minus I. It's not written, but it is there. They always come in pairs. So how do you write this polynomial with rational coefficients? Essentially what you're doing is you're now working your way backwards. Before, you were given the polynomial, you factored it, you said each factor equals 0, and you solved and you got x equals your 0. Now you're starting with the x equals your 0 part, and you have to work backwards. So to do that, what you're going to do is you're going to write every single one of your zeros as a factor. So when you do that, that's going to be x minus 3. Because think about it, you said x minus 3 equal to 0, you would add 3 over, correct? For the imaginary ones and the complex ones, it's still going to be x minus that particular 0. And again, x minus that particular 0. Because again, if I were to set this equal to 0, that factor, I would add that over and get 1 plus I, would I not? So x minus your 0. So to continue to write my polynomial with rational coefficients, all I need to do now is I need to multiply. Okay, I need to actually expand out all 3 of these in the orange. I need to multiply them. My suggestion to you, to make it so much easier on yourself, always multiply the imaginary parts together first, and then multiply the real parts in. So then that way, when you multiply 2 imaginary factors together, you'll always should end up with real coefficients. No imaginaries. All the imaginaries must be gone if you multiply them out. So if you do them first, now you're only dealing with real ones. So take your time. What I'm going to do is I am going to distribute that negative over. So it's going to be x minus 1 minus I. And I'm going to do the same thing with the other factor. X minus 1 plus I. By distributing over the negative, I'm now able to multiply every element in the first parentheses to every element in the second parentheses. X times x is x squared. X times negative 1 is negative x. X times I becomes an ix. Negative 1 times x is a negative x. Negative 1 times negative 1 is a positive 1. And negative 1 times I is a negative I. Last but not least, negative I times x, that's a negative ix. Negative I times a negative 1 is a positive I. And negative I times I is a negative I squared. All I've done is literally multiply every element in the first parentheses to every element in the second parentheses. Notice anything? Some things cancel out.
The IX's can cancel out.
The IX's cancel out, and
I squared is negative 1.
yes, I wonder if anybody remember that from algebra 2. I squared is a -1. Okay, that's your powers of I. So that is gone. And then what else? What else goes away?
I.
The i's as well. So the only thing I'm left with now is an x squared, a negative x, a 1, and then this -1, which is technically a +1. So when I multiply those two imaginary factors, I end up with x squared minus 2x plus 2. No more imaginary parts, real coefficients. And now multiplying it by x minus 3 is going to be a breeze to do. Because I still got to multiply by that last factor. Okay? So I'm going to go distribute. X times x squared is x to the third. X times -2x is a -2x squared. X times 2 is a 2x. -3 times x squared is a -3x squared. -3 times -2x is a 6x. And -3 times 2 is a -6. When I combine like terms, I have x to the third minus 5x squared plus 8x minus 6. This is my cubic polynomial that if I were to factor this out and solve it, the roots would be 3, 1 plus I, and 1 minus I. There is a way to check, but that's for the last section of this unit. Write a blank polynomial with rational coefficients with roots of 5 and -3 plus 2i. What degree is this going to be?
Cubic.
It's going to be another cubic. Because my zeros are 5, -3 plus 2i, and
-3 minus 2i.
good. So remember, we write those as factors. Of course, the real one is going to be x minus 5. This imaginary one's going to be x minus parenthesis -3 plus 2i. And then this last one's going to be another x minus, but this time it's -3 minus 2i. When I distribute over the negative. So the thing is that we want to make sure that we change the imaginary parts for our 2 zeros. It's always going to be x minus, but when we distribute it over, the 3's are going to turn positive, but the 2 i's will be different signs. So I want you guys to try to multiply this out on your own. Let's see if we end up with the same answer, okay? So go ahead and multiply this out. Give me my polynomial with rational coefficients. Now remember, there are any complex zeros or imaginary zeros, when you multiply them out, you should end up with only real coefficients with the polynomial when you multiply it. If you don't, that means something happened, okay? Distribute over that negative. Distribute the x. The 3. Go too big again. And that -2i. My 2i x's should cancel out. My 6i should cancel out. And that -4i squared should turn into a +4. So I should have x squared plus 6x plus 4 when I multiply that out. Did I miss some more? Oh, not 4, sorry. 13. Got the 9. 9 and 4 make 13. my mistake. Looking at your faces, y'all were like, no. I was like, uh-oh, mistake somewhere. Multiply that by an x minus 5. That's actually how I do that part. Stack it, I can see it a little bit easier when I need to add it. You don't have to do that, that's just what I do. So you should add x to the third plus x squared minus 17x minus 65 as your answer for your polynomial. So double check if you didn't get those coefficients. Maybe it might have been somewhere where you made a mistake. Maybe you put down 4 and you should have been a 13, like me. I didn't catch it. Oh. We got 2 more. Next one, give you a little bit of a break. I give you all real roots, but I told you that -1 is a double root. What does that mean, double root? Not plus or minus. It's one zero that's basically stacked on top of another 0. So it means that there's 2 of them, hence the double root part, okay? So I have 6, -1, another -1, and then a 2. So I'm writing a what degree polynomial? A 4th degree polynomial. Quartic. So again, a double root basically means that that 0 shows up twice. That 0 shows up twice. As a multiplicity of 2, that means it actually touches at -1, this polynomial. All right? I want you to write the factors. I want you to give me the polynomial. Okay? These are all real. Let me see if you can write the factors. Let me see if you can give me my polynomial. Or you guys want to do the factor part together? You want to try? Give it a try. Jemima, what's one of my factors? Are you still with me, Jemima? Oh no. She might still be with me. And give me one of my factors. X minus 6. Elizabeth, what's another one of my factors?
X plus 1.
X plus 1. I actually have that one twice. And then the last one, X minus 2. Okay? But it doesn't matter which ones you multiply together first because they're all real and they all got to get multiplied with each other eventually. Okay? So maybe our intermediate steps might not be the same, but our final answer should still be the same. So I'm just going to multiply the first 2 because they're right beside each other. It's going to give me x squared. A 1x and a -6x gives me a -5x minus 6. When I multiply the last 2, that's x squared. A -2x and a 1x give me a -x minus 2. And so then when I multiply this together, every element of this first parentheses has to be multiplied to every element in that second parentheses. So that's x to the 4th minus x to the 3rd minus 2x squared minus 5x to the 3rd minus 6x squared plus, nope, sorry. Got distracted. Back it up, back it up, back it up. Minus 5x squared plus 5x squared plus 10x, and then -6x squared plus 6x plus 12. So your final answer should be x to the 4th minus 6x to the 3rd minus 3x squared plus 16x plus 12. Yes?
Yeah.
In your homework, I've basically provided you with the x to the fourth, the x to the third, the x to the second, the x, and then everywhere else are blanks. So you just have to fill in the coefficients. So the coefficient you would fill in here would be a what? A 1. Every single one of them has a plus, like that connects them together. So if your coefficient is a negative, you have to type in -6. So it's going to look like plus blank. You would have to do -6. That's what you would type in. Okay? Then -3. Then 16. Don't type in plus 16 because there's a plus already there. Okay? And then a 12. All right? So I've already provided like the template for you. You just have to fill everything in. Okay? Last one. This one we got a complex and an imaginary. Okay? Complex number and an imaginary number. So if root 3 is one of my roots, then I know what else is a root.
Negative root 3.
Very good. And then if 4i is a root, then so this is going to be yet another 4th degree polynomial. My factors would be x minus root 3. So you know if I set that equal to 0, I get a positive. This one would be x minus a negative root 3, which would turn into a plus. Then I'll have x minus 4i. And then my last one would be an x minus a negative 4i, which is a plus 4i. Then I'll multiply everything out. And the beauty about these, x times x is x squared. X times root 3 is an x root 3. Negative root 3 times x is a negative x root 3. And then a negative root 3 times a positive root 3 is a negative 3. Because technically, give me a negative root 9. The square root of 9 is 3. Okay? The inner term and the outer term, when I FOIL, does what? Goes away. So I'm just left with x squared minus 3, which is so nice. Same thing happens over here when I multiply the x minus 4i and the x plus 4i. I'll get x squared plus 4ix minus 4ix minus 16i squared. Again, my inner and my outer term cancel out. I squared is equal to,
-1.
so then this becomes just x squared plus 16, because again, I squared is -1. Negative 16 times -1 is 16. So then I'm just multiplying those two binomials together. That's going to be x to the 4th plus 16x squared minus 3x squared minus 48. So when I combine like terms, x to the 4th plus 13x squared minus 48 is my final answer. So it works the same way with the radical roots. If this was on your homework, what would you type into this first blank?
1.
Into the second blank?
16.
0. Because
Oh.
I don't have a third term. It's gone. What will go here? And then here? What about here? Negative 48, because there was a minus there. Okay? So on ones like this, when I'm missing a term, it's still gonna have a blank there. Don't put none, 0. Okay. Yes, sir.
This is less than 3 points.
If you notice, there was no number there because when I made this, I lost count of where we were. I think this is 3, 5.
Pretty sure.
I think we're on 3, 5.
I think the next one's 6.
Okay.
Just did 3.
Yeah. Okay. So we're up there. So this is 3, 5. This one's a long one. I think we go all the way up to 8 or 9. So yeah, this unit's a long one. But this is how you can write polynomial equations from their roots. All this ties in together. Okay. From this with the graphing, we graph polynomial equations. Okay. Now we're taking the zeros and we're writing them. Soon I'm going to give you a polynomial equation. I'm going to ask you to find the zeros of the more complicated ones, not the quadratics. I'm talking about ones like this, or ones that are to the 7th power. Okay? So all of this is about functions, polynomial functions, functions. Are there any questions about conjugate root theorem or Descartes' rule, which tells us how many possible positive and negative real ones we'll have?
Is this still preparing us for like the actual calculus, or is this like calculus work?
This is foundational stuff.
Foundation stuff.
Yeah, it's foundational stuff.